In this video, we're going to be talking about simple linear regression and correlation inferential methods. So suppose we were to investigate the relationship between y equals the first year college grade point average and x equals the high school grade point average. Is the first year college grade point average determined solely by the high school grade point average? So a relationship in which the value of y is completely determined by the value of an independent variable x is called a deterministic relationship. The first year college grad point average and the high school grade point average do not have a deterministic relationship. A description of the relationship between two variables that are not deterministically related can be given by a probabilistic model. So the equation for an additive probabilistic model is y equals the deterministic function of x plus the random deviation, which is our f of x plus e, where e is an error variable. Now the simple linear regression model assumes that there is a line with y-intercept alpha and slope beta, called the population regression line. When a value of the independent variable x is fixed and an observation on the dependent variable y is made, then y equals alpha plus beta x plus e. Without the random deviation e in the equation, all observed x and y points would fall exactly on the population regression line. So here we have our alpha, and here we have the population regression line with our slope beta. Here we have our points, which would be e sub 1 and e sub 2. Basic assumptions of the simple linear regression model are that 1, the distribution of e at any particular x value has a mean value of 0. So that's to say that mu sub e equals 0. Second, that the standard deviation of e is the same for any particular value of x. So this standard deviation is denoted by sigma. And then third, the distribution of e at any particular value of x is normal. And 4, the random deviations e sub 1, e sub 2, all the way to e sub n associated with different observations are independent of one another. So let's look at an example. So we're going to look at the heights and weights of a population of adult women. So notice that on the horizontal axis we have heights, and our vertical axis we have weight. How much would an adult female weigh if she were 5 feet tall? So height here is in inches. So the weights of women that are 5 feet tall will vary. In other words, there is a distribution of weights for adult females who are 5 feet tall. So are some of these weights more likely than others? And what would this distribution look like? This distribution is normally distributed. So what would you expect for other heights, like 64 inches? Well, we would expect to have a same thing, that normal distribution. And for 68, the same thing. Now, where would you expect the population regression line to be? We should find them here. Now, notice that if we were to draw a straight line kind of right here, that this would correspond with our mean value approximately for each. Now, we want the standard deviations of all of these normal distributions to be the same. So basic assumptions of the simple linear regression model revisited. So let's come back to this. Now, remember that the variable e is a measure of the extent that individual y values deviate from the population regression line. As far as our sigma goes, for any particular x value, the standard deviation of y equals the standard deviation of e. The distribution of y at any particular value of x is normal. Now, we use y hat equals a plus bx to estimate the true population regression line, where b is the point estimate of beta. So we're going to have our s sub xy divided by our s sub xx. Our a is the point estimate of alpha, which is y bar minus b times x bar, where s sub xy equals the sum of x times y minus the sum of x times the sum of y, all divided by n. And the sum and s sub x times x is going to be the sum of x squared minus the sum of x squared divided by n. So we're going to let this x star denote a specific value of the predictor variable x. So then a plus b x star has two different interpretations. One, it is the point estimate of the mean y value when x equals x star, and it is a point prediction of an individual y value to be observed when x equals x star. Let's look at an example. So medical researchers have noted that adolescent females are much more likely to deliver low birth weight babies than are adult females. So because low birth weight babies have higher mortality rates, a number of studies have examined the relationship between birth weight and mother's age for babies born to young mothers. So the following data is on X equals the maternal age in years, and that Y equals the birth weight of the baby in grams. And so here we have our data. So we want to sketch a scatter plot of these data points. So doing so is going to give us the following display. Now the scatter plot shows a linear pattern, and the spread in the Y values appears to be similar across the range of the X values. Now this supports the appropriateness of the simple linear regression model. So summary statistics computed from the sample data are our n equals 10, because we have our 10 samples. So the sum of x equals 170, and the sum of our y equals 30,041. So then we're going to take the sum of our x squared, and then we get 2,910, and the sum of x times y, which is 515,600, and then the sum of our y squareds, which is 91,785,351. So we're going to be using these summary statistics. So to find our values, so our s sub xy, using those values comes out to 4,903. Our s sub xx equals 20.0. Our b is 245.15. And our a value comes out to negative 1,163.45. If you need to, now would be a good time to pause the video and try plugging in those test statistics and see if you can get the same values as well. Now the estimated regression line is y hat equals negative 1,163.45 plus 245.15x. So let's go back to our scatter plot and let's put our y hat equation there as well, our linear regression model. Now this 245.15, that's the weight of babies. And it increases approximately 245.15 grams for each increase of 1 year in a mother's age. So what is the point estimate for the mean weight of babies born to 18-year-old mothers? So basically we're going to take the 18 and plug it into our x value and see what we get. And we get that mean value is 3,249.25 grams. Now this point is the point estimate for the mean weight of all babies born to 18-year-old mothers. This is also the prediction of the weight of a single baby born to a mother 18 years of age. A statistic for estimating the variance of sigma squared, right, because that's our variance, sigma squared, is going to be our S sub E squared equals our SS resid divided by n minus 2, where our SS residual is the sum of y minus y hat quantities squared. Now, the subscript E reminds us that we are estimating the variance of the errors or the residuals. So the estimate for the standard deviation is going to be S sub E equals the square root of S sub E squared. Now note that the degrees of freedom associated with estimating our variance or our standard deviation in simple linear regression is n minus 2. So not n minus 1 like we've used before, but n minus 2. So why n minus 2? Well, since we must estimate for both alpha and beta in the regression line, we reduce the sample size n by 2. So recall that the coefficient of determination, our r squared, is the proportion of observed y variation that is attributed to the model relationship. Let's go back to our scatter plot. So if we want to find our SS residual and our SS total, we plug those in, because remember we have those values, and that's going to give us 426,762.45 for our SS residual. And our SS total will be 1,780,322.9. So we use this to compute our S sub E, so our standard deviation, and our R squared, so our correlation coefficient. So we plug those values in. Remember that we had 10 samples, so our degrees of freedom here is 8. So our standard deviation is 230.97 for our sample, and our correlation coefficient is 0.76. So for a particular mother's age, the typical deviation for possible weights of babies is approximately 231 grams. And approximately 76% of the variability observed, weights of babies can be explained by this model.